I bet $2. I'm not going to get paid. I bet $20. I'm not going to get paid.
Wait, I'm not showing up at 7:30. Let's make that clear. Yeah, that's it. If I'm showing up, it's at 3 and it's at $4.
What are you doing, Gavin? You're talking about I have no idea what I'm asking. Alright guys, so back at the workspace. Hello, my name is. Back at the workspace. Back at the workspace.
Oh, I didn't bring my book.
We were challenging each other about how much we're going to buy at Chick-fil-A tonight, right?
I'm betting how much I'm not going to pay. I'm going to
Yay! Between 5 and 8?
Yes.
Same heritage Christian?
Yes, this is the only time I have to go because my mom.
Did you like it spurred?
Actually, maybe I'll do like a first dinner at 3 and then I'll go back at 8.
Bro, I want to drive me to Chick-fil-A.
Now we're talking about Chick-fil-A. Have you eaten?
We always take
like I want to see like how can I get the best conditions. Yeah.
and yellow
So,
fest.
Take it. If you like titling this in your workspace, section 2.2 exploration. Technically, theorem number 5 means nothing to you, right? Like, what's theorem 5? So instead, you could say exploring the limit properties. Exploring the limit properties. That's what theorem 5 is. We'll see in a second. Yesterday, we ended with squeeze theorem in our notes. We'll go back, we'll talk about it. But to start off today, in your workspace, back in your homework spiral, this is 2.2, exploring limit properties. I want you guys, you can work in your groups. However, the discussion needs to stay in your groups, aka my people who are loud talkers. Please quiet it down so that only you are talking in your groups. I want you to work through numbers 1, 2, 3, and 4. And BS, I think you need your graphing calculator.
Oh, you guys
Or do you? Nah. You can have it as a backup if you need to use the table. You can have it as a backup if you need to use the table. But you are going to infinity. You don't have tons of time, but think it through. How would you answer 1 and 2 and 3 and 4? And if you get those, go ahead and try to solve 1 and 2 and 3. Let's start.
So I think
You're just answering 1 through 4. Exploring limit properties. If you get bored and you're done, then you can.
wait, isn't this an
Okay.
improvement, though?
Don't we normally do what's on top first and then what's on bottom?
Like, isn't sign of infinity?
Well, you know what assuming makes you.
Or X pushing infinity.
Silly. It makes you silly. Okay, go.
Is sign of X approaches infinity?
Do you want me to put the coffee on the timer
Sign of X
or whatever we're doing and have it ready hot coffee? Or do you want me to make it Thursday? Let it
Oh,
cool
is
down
that
so we have
number
nice coffee.
1? Oh, never mind.
That's not correct, right?
Do they exist?
May I go on my phone to this character?
Yeah, like when you like
That'd be good. Does the limit of the quotient exist?
Alright, so I think the limit for f of x exists because as you keep plugging in f of x, yes, limit exists because you plug in infinite x and you get infinity, and then you just plug in infinite x inside x and you get whatever number. So it's infinity plus whatever number, and that's how it happens. So I think so. It makes sense to me. Yeah,
It's like what about wait, because this oh no, because science. This is the second. Oh no, because science grid X versus
yeah,
science grid X
you
is
just
one.
yeah.
So like
Limit
we need to say the limit as
infinity
infinity
of
one.
x.
It's just one.
Yeah, just x.
Do you understand
What?
do you understand why?
Yeah.
Limit.
Nothing.
Sure, what?
Oh, we didn't know. So we're just checking. Okay, next one. What about that?
Oh, can you apply?
Well, remember, we're like,
Okay, you know what? Let's move on.
No. Maybe.
But this is 5x plus that. So like, now everything feels wrong ever since yesterday. So I'm afraid to help.
Okay, so it says limit.
wait.
Google it. You have Siri?
I don't have Siri.
Somebody in your group does.
Okay, Google.
We're on number
Respond.
Your entire group only has Google Phones?
Oh gosh.
Oh, I was gonna be like, no, what?
Yeah, but I don't know what to do anymore. I'm like, actually confused.
Doesn't even respond.
It's so funny. I do it.
I don't think there's 3 people in the world.
Oh yeah, see if I can add.
Okay.
Yeah.
I'll prove you wrong. My family has Google Phones.
Wait, no.
Okay, record that.
I'm not judging yours. I was just surprised if your whole group had Google Phones. So
You're wrong. My family has Google Phones.
Oh,
you need to call it weird.
Your brother is ratified.
Wait. Can we make it two
Buddy, you got a smartphone.
So it becomes like
I can do math problems anytime.
2x. Because the one says f of x minus g.
only vectors, right?
So I'll land in the
You guys done? No, we need help. Oh.
It would be ln of 2x over x plus 1.
Nothing productive at all whatsoever.
Yeah.
Did anybody look up Ratify?
I found out.
Did you share it with the rest of the class? What is Ratify?
Sine x times sine x.
Sign or gift also.
So if you plug infinity into sine x, then you get infinity, right? Alright, what is the limit of sine x? We need to get this established because
Okay, so Victor's gone
walking
today.
on a tightrope. Victor is doing a driver's test.
Yes. I didn't know that.
No,
But now I
no,
do.
that's for finding a point. If it was limit x goes to 0, it would be infinity. But this is for infinity.
But like when you plug in,
So
He
I
drives
keep going
a
this way.
lot.
What is it
I was
approach?
surprised he did.
when you plug in
Yeah, what is it?
ln x
and
plus
then for gfx,
Oh, wait, sine x squared, it equals 1.
Alright, meeting Gavin, let's see how they did. They were working semi
Yeah.
well.
Uh,
Very talking. According to AJ, we were very talking. Okay.
behavior is
Alright, if you guys want to see what theorem number 5 is, here's what theorem number 5 is. It's something that I usually show you and you're like, it's easy. They give you that, and you plug and chug and you're done. However, this might have not been quite so easy because it was exploring that theorem and going a little bit more in depth. So, what if they gave you 5x plus sine of x and x, so two different functions? functions, they ask the question, you're going to infinity, does the limit of both exist? What did you guys answer for that first part? Yes? So what was the limit as x goes to infinity of f? Positive infinity. What was the limit as x goes to infinity of g? Okay, but wait a minute. How did you take his limit? I thought sine of infinity didn't exist. Well, it is a value. It's between 1 and negative 1. It just doesn't get closer and closer to a single value. But who was stronger than sine of x? 5x. And what's 5x doing regardless of sine's little issues? It's going to infinity, right? So this overruns that. That going between 1 and negative 1 isn't going to hold him back. So yeah, the limit is infinity. Now that's more of an idea, conceptual understanding, but yeah, that works. And then the limit of x is also infinity. Good. So can we apply the quotient rule? Quotient rule meaning, some of you were doing differentiation stuff. It was just the quotient limit property. Can we apply the quotient rule, the quotient limit property, to limit as x goes to infinity of f over g? So what happens if we try to go infinity to infinity? What do you guys say? Because over here, if you take it, don't you just do that one over that one? So infinity over infinity, it's 1. Can we apply the quotient rule and just take the limit over the limit and say yay? No. So these properties maybe only apply to constants or maybe only sometimes to infinite limits? What ends up happening when you are taking the limit of the quotient? It's 5. Why is it 5? You could do L'Hopital's. Or you could explore in a table.
Factors of the leading coefficient.
Or some other ways. But basically, what are the strongest? What's wrong? Okay. What are the strongest, right? Whenever we do degree tests, whenever we are trying to go to infinity, considering the magnitude of the numerator and the denominator, didn't we say 5x was the strongest?
Yes.
Didn't we say x was the strongest?
Yes.
Aren't the degrees tied? And the ratio of leading coefficients is going to be 5. How could you back me up and make sure that's true? Go to a table and plug it in, the f over the g or the y1 over the y2. Guess what you're going to see as you plug in 10 and 100 and 1,000 and a million? It's getting closer and closer to 5. But would you have gotten that necessarily by doing infinity over infinity? Nope. How about number 2? Sine squared, cosine squared. What's going on as x goes to infinity of each of these? Both of them? So f approaches infinity? And g approaches infinity? Are you sure? I thought sine and cosine go between 1 and negative 1. What happens when you square values between 1 and negative 1? It goes between 0 and 1. So what happens as x goes to infinity? Isn't that guy oscillating between 0 and 1? Isn't that guy oscillating between 0 and 1? Not negative 1, because if you square it, it can't go negative. So isn't this technically not existing and this not existing because they can't settle on anything? They're not converging to any single value? Oh, stink. So, hey, does the sum rule work? If you add a dne plus a dne, you get dne? No. What's the limit if you do sine squared plus cosine squared? Sine squared plus cosine squared is 1, so the limit of 1 is 1 as you go to infinity.
We were all right.
So separately, their limits don't agree, but put them together and their limit does? That's weird. Number 3. What's going on as I go to infinity of ln of 2x or ln of x plus 1? Now, I know you guys don't have it perfectly down, but you know generally ln, right? And just because they throw in a coefficient, just because they throw in a plus 1, does it really change what's going on to infinity? Not too much. So where are they both going? F's approaching infinity and g's approaching infinity. True? What about the difference rule? So infinity minus infinity is 0. No, it's indeterminate. It's indeterminate. Who knows? Who's stronger? Okay, but hold on. What's another way of thinking about it? How could you have thought about the limit of f minus g?
ln of 2x over x.
Yeah, aren't there ln properties?
You told me.
And with ln properties, aren't you allowed to take the difference of two ln's and happens as you go to infinity? Isn't there a property that says, hey, if you have a composite function, oh, where is he? Is he not up here? We should sue.
Yes.
He's in the AB notes. Struggle. There's usually one, the limit as x approaches, well, basically a constant c. I guess you could also throw in the infinity in this case, of an f of g of x is equal to f of the limit. Maybe they wrote it somewhere else, so they're not putting it here. But we could actually take that ln and take it out as long as f and g are continuous functions on the domain, which ln is as we go to positive infinity. I can take that ln out. I can take the limit of the inside. Aren't my degrees tied? So the ratio of leading coefficients would be 2. And then bring the ln in. Do these properties always apply? What are some things that were happening in the pieces that made it to where we couldn't just put them together to get the answer, the value? What do we have to watch out for? DNEs and infinities. Yeah, DNEs and infinities. Which you guys already kind of knew if you're doing like infinity plus infinity, infinity minus infinity. Well, the first one we should be able to do. Infinity divided by infinity. Like there are indeterminate forms that we have to watch out for. So we have to watch out for indeterminates and DNEs. Because this one was super weird. DNE, put it together, it's 1. Huh? So you have to be a little bit careful. Now, I apologize because I guess I really did just write these down. But I wanted you guys to actually read the words. So this was the limit problem you were solving for 1. This was the limit problem for 2. This was the limit problem for 3. But hold on, number 4 says put it all together. But first, there's a question. Joe Tan, go for it.
When you L'Hopital it, you get 5 plus cosine x. When is that approaching? And like, that's not.
But when you plug in, is it an indeterminate form that needs L'Hopital's? Is it legal to use L'Hopital's? Because you would have infinity plus or minus 1 all over infinity. Infinity over infinity would be indeterminate. You know, 5 plus cosine x. 5 going in between 1 and negative 1. It's going to be oscillating. Joe's really quickly debating number 1 as to whether or not that one's true. Can I do it in algebraic way instead of a... One quick thing to note with L'Hopital's, and I might be incorrect, but x going to infinity might make it not apply. Hold on, let's see. So if we have 5x plus sin x. I'm going to go algebraic. Because algebraically to go to infinity, you multiply by all of the strongest, which would be 5 plus sine of x all over 1. As I go to infinity, that's 0, right? Because the denominator is going to win. That's an algebraic proof as to why the limit is 5. Your question is, why does L'Hopital's not apply? L'Hopital says that f and g both have to be continuous functions, right? And then the limit results in an indeterminate form. We might have to research, Joe, as to whether or not L'Hopital's only exists as you go to a constant. There might be corollaries if it goes to infinity. That's a good question, though. We would have 5 plus cosine, and cosine is going to oscillate. And as cosine oscillates, it's going to take away from the 5. And so I see why you would have said DNE using L'Hopital's. So that's my question with L'Hopital's. It's not the question of today, but that is a question we could visit. So remember that one for me. Okay. But does my algebraic proof make sense? Yeah. So what did you guys come up with for number 4? What advice might you give when applying theorem 5? This is technically what we were supposed to start down, or start off today writing down. What do we need to be careful of?
Check the degrees.
Check the degrees. Okay, that could be helpful. Watch out for expressions with trig. When going to, like, all of these are going to infinities, so it's not just the normal going to a constant, which is my question with L'Hopital's. Watch out for the DNEs. Yeah, I would put a quick little, okay, this theorem is great and all, but watch out for L's and M's that are DNE or infinity. Which I think you guys would naturally do, because you know to shy away from or to not have an answer when seeing infinity over infinity or infinity minus infinity. But you might have been like, DNE plus DNE is DNE, yay! Which it wasn't, it was 1. But not in every context, just in the sine squared of x plus cosine squared of x context. So yeah, that's kind of just a little like, okay, these are great, these are good, these usually work, but we have to be careful. And one of the ways that you guys know that we have to be careful, maybe not as well as hopefully you will, is with the whole L'Hopital's thing, which ironically Joe brought up. And now we have a question about x approaching with L'Hopital's and if that makes a difference, x approaching C or x approaching an infinity. However, in AB, here's something interesting. I gave them these cute little flip books for finding limits this year. I don't know, something just to be memorable, to be different, to have a little bit more fun. I don't know. But in these little flip books, I did find a couple things interesting. When they did the basic rules, first of all, they didn't do the whole L and M or L and K, what we did last year. But what they did actually perfectly sets up how we should be showing work for L'Hopital's. How we should be splitting it up to the limit of the top and the limit of the bottom. And technically, I think in the book this year, and I don't think it's in BC, I think it's in AB. AB's properties has a very specific qualifier at the very beginning of these properties that talks about f and g being continuous functions, which are exactly what the AP readers want to see when you're doing a L'Hopital's problem. Like, hey, f is continuous at, g is continuous at, sweet, we can do this, and let's go. So there are some, it's just not all textbooks are created equal, and my way of shortening things can sometimes get us in trouble. L'Hopital's is one of those places, one of those ways. So we actually have another L'Hopital's thing to add to our, let's make sure that we know it and know it well this year. We're actually not learning L'Hopital's right this second, but it's something for us just to keep in mind. Let's go back to the squeeze theorem yesterday, because I lost some of you. I lost some of you hardcore. So I'm going to zoom in on this example. We did all of that. Horizontal asymptote, I think you guys are okay with in the sense of a horizontal asymptote occurs if I'm coming from the left. Now, I was very specific. I had to reword this. And or the right. Maybe going to the left and the right gives you the same one, but maybe you can have two different ones. The AP loves to be tricky with that. We have to be careful with absolute value and square roots. There could be some plus or minus stuff going on. But specifically, what we were more confused on yesterday was the squeeze theorem. So the squeeze theorem also holds for going to positive and negative infinity, in that the squeeze theorem isn't just for going to x approaches c, but also for x approaching positive, negative infinity. So I threw in this example yesterday, and if you were to look at this example yesterday, and if you were to plug in, it would have been a bit confusing to try to solve, because we could have plugged in infinity to cosine, but it doesn't exist. It's always oscillating. It's always confused. We could have plugged in infinity to the bottom, so maybe we would have thought of something like, hey, okay, well, this guy's kind of just bouncing around, but that guy's getting bigger. So maybe your brains would have said the degree on the bottom is stronger, so the limit is 0. But a mathematical justification for that, beyond just like, well, cosine stuck, so forget him, x squared wins, could have been just to say, okay, I know something about cosine. I know cosine goes between -1 to 1. Now, maybe my absolute value notation confused some of you. I didn't mean to. So if it's a little bit nicer, we can say that cosine of x is going to be in between -1 and 1. As a result, if I do 1 minus every expression, keeping everything balanced, 1 minus -1 is going to be 2. Well, hold on. 1 minus is going to be a little bit iffy. We'd have to multiply everyone by a negative first, which would flip my inequalities, and then I'd have to add 1. But pretty quickly, we could get to 1 minus cosine of x being between 0 and 2. So if you we wanted, we could have done a little bit of math. Could have multiplied everybody by a negative. When I would have done that, that would have flipped, and that would have flipped. Then I could have done plus 1, plus 1, plus 1. And that's how I get my 0 on one side, my 2 on the other side, and my 1 minus cosine on the inside. Or you can just think of what's 1 minus negative 1. There we go. What's 1 minus 0? There we go. And as a result of that, I can come back to this expression and say, okay, well then this is going to be in between that 0 and 2. My denominators can all stay the same. I can have this function, what I'm trying to take the limit of, be squeezed in between 0 and 2 over x squared. The limit of 0 as I go to infinity is 0. The limit of 2 over x squared as I go to infinity is 0. So what must be squeezed in between? This guy. So his limit is going to be 0 as well. Once again, some of you could have done like the bottom wins and gotten to 0 faster. I was just showing how the squeeze theorem could be applied, especially when, or easily when, you have cosines, sines, because then you can always squeeze them because they're always oscillating between 1 and negative 1. And you can start kind of setting up expressions, and with that squeezing, it's easier to take the limits of the ends and then figure out what the guy in the middle is also doing. So anyway, squeeze theorem comes back. He's going to kind of just randomly poke his head in every now and then as we go throughout. And yes, we should probably think about that AP guy from last year. You said it was FRQ, right? The squeeze theorem? Okay. So I'll have to look at him for sure. But beyond that, this section is all about limits involving infinity. So we could be going to infinity or to negative infinity, which means looking for horizontal asymptotes if they exist. But we could also be coming in towards a constant, specifically towards a vertical asymptote, and we'd be getting infinities there also. So we're either going to infinities or we're coming in towards a vertical asymptote, and we're going to get infinities also. So if I was to ask you, when do you get an infinite limit when x is approaching a constant? If I was to ask you, when would you get an infinite limit when x is approaching a constant? What would you guys answer? When there's a vertical asymptote. And so then if an AB guy or girl was to ask you, when does a limit equal infinity? How would you tell them, hey, watch out for, whenever this happens, now don't just tell them vertical asymptote, they don't know graphs. I mean, you guys barely know graphs, right? Huh? Maybe domain problems, but can't domain problems also be holes? And for holes, the limit exists and equals a constant. Gotta be more specific. If they ask you, well, when will a limit equal infinity?
When the degree at the top is stronger than the bottom?
Possibly. But I could actually write up an example right now where the degree of the top is stronger than the degree of the bottom, and the degree of the bottom, every factor matches with the top, so they're only holes. Now, as I go to infinity, Kevin, you're right, it would be infinite. But what if they're asking, when would the limit equal infinity, and they're not talking about end behavior? Joe?
When you plug the C in and then it becomes
Number of these. Yeah. If they see x approaching infinity or negative infinity, most brains are kind of like, it could be going up, it could be going down, it could be like converging to some sort of horizontal asymptote. But where they're going to get confused, when can a limit equal infinity? When it just looks normal? When you get a number over 0, right? So number over 0 last year, that's not keep going, right? What did we write as our reminder? Plus or minus infinity, check the sign. True? But the dilemma is, if it's a vertical asymptote, couldn't the one-sided limits agree? Limit is positive infinity. Agree? Limit is negative infinity. Or disagree, and the limit does not exist. So what do I have to do with any vertical asymptote? If I realize it's a vertical asymptote, test both sides. And I'm making a huge point of showing that notation this year. I don't remember, to be totally honest, if I did last year. Maybe we talked about it for sure. But in order for the limit to exist, the one-sided limits must agree, and in order to know that, we have to check the one-sided limits. One side of the vertical asymptote, the other side of the vertical asymptote. But your life will be so much easier. So much easier. If you can remember. If you can remember that plus or minus infinity means only check sign. You don't have to make a table. You don't have to do crazy stuff with decimals. You just have to check the sign. Because anytime we figure out a vertical asymptote, wait a minute, why is this a vertical asymptote? Isn't it just a value when you plug it in? What sign of pi over x? Or pi over 6? 1/2, it's a little baby one. 1/2? All over? Okay, so that's plus or minus infinity, check the sign, right? If you want the AP guy to ignore it, just put a little X through it and be like, hey, you can't grade me wrong. Just don't put an equals, you'll be okay. We can't say equals because that means the NE. The function value does not exist. There is a discontinuity at pi over 6. But that tells me it's a vertical asymptote. So if I'm going to come from below pi over 6, I'm just lazy, so I'm putting f of x, and I'm coming from above pi over 6. But some of you would start stressing out right about now. Either because of the unit circle, or because of a table. But we know the answer to each of these. The answer is some sort of infinity. What we need to figure out is it plus or is it minus? It can't be both. It's going to be one or the other, so we have to check the sign. Now here's a dilemma. What's something below pi over 6? Pi over 8, pi over 9, pi over 12. It's not in the unit circle. But the question is, whatever you pick, pi over 8, pi over 9, pi over 12, something that's littler than pi over 6, what is the sign still going to be? What sign is it going to have? Positive. All the signs in the first quadrant, even if babier angles than pi over 6, are going to be positive. But what's going to happen if I'm doing pi over 8 minus, or pi over 9 minus, or pi over 12 minus? Negative. So what is this one? Negative infinity. But what if I come from the other side? Oh, that's easier. Pi over 3, pi over 4, pi. It doesn't matter. Sign in the first quadrant will be positive, and any bigger angle is going to be. So what's my final limit? From that side, positive, but put it all together, my limit does not exist. Why? Because it's one of those weird at pi over 6. From below, somehow he's going down, and from above, somehow he's going up. It's one of those ones. But did I actually have to plug in pi over 9, pi over 12, and figure out what sign is? Why? All I'm doing is checking the sign whenever I see, ooh, what's his name? What form is that? Not indeterminate, but infinite. It's still an iffy form. Like, I wouldn't say determinate. We can determine it's a vertical asymptote, but infinite term, oh brother, infinite form. I wrote what I said instead of. There we go. So we have to check the one-sided limits and see if they agree. Check the one-sided limits and see if they agree. I don't like him being red. I'm going to change him. Okay. Now here's something new. I kind of brought him up a little bit last year, but not tons and tons and tons. And some of you might appreciate this because this term might have actually helped us with that whole 5x plus sine of x over x thing, as far as having some vocab to actually refer to it. Because this says, well, there's actually a term for considering just the highest degrees. It's actually a function that we can think about as we're going to the right, as we're going to the left. If we're ignoring all of the lesser terms and only focusing on those for whom the magnitude will be determined, or from whom the magnitude will be determined. We can call them end behavior models. Maybe it's something helpful that I should introduce the vocab to AV, but the book doesn't use it, and for me to use it, it might be helpful for infinite limits and doing degree tests. For you guys, basically, there's just an actual mathematical way of talking about this. To find the limit as x goes to infinity of an f over g, consider the right end behavior model. That limit will be the same. Now careful. This might not make sense unless you realize who's who. So the function g is our end behavior model. To the right or to the left. And it's for some given function f. So you're given some f, you're comparing it to some g. And that g is going to have the exact same limit. The ratio of the two limits is going to be 1. So aka we can take the limit of the right end behavior model and know the end behavior of f, or take the limit of the left end behavior model and know the end behavior of left on the left side. So let me show you an example, given what we've already done. If we go back to f of x is equal to 5x plus sine of x all over x. Your g, your actually right and left end behavior would just be 5. Specifically 5x over x. With that little sign, yes, there are going to be some places where it's a little bit off, but in essence, as you go to the right end or as you go to the left end, as you get farther and farther away from the origin, as 5x is increasing or decreasing without bound, as x is increasing or decreasing without bound, the sign is of very little significance, and it gets smaller and smaller and smaller in the impact that it's making. So what's going to go on at the right end? 5. What's going to go on the left end? 5. And how did I get that? I looked at the strongest magnitudes of the numerator and denominator, and I took the ratio. So when I have you guys take the ratio of the leading coefficients, what I actually have you doing is building a right end behavior model or a left end behavior model and taking that limit, technically. The only time we get in trouble, which is why I had to say watch out, watch out, watch out, watch out during AB, is when I have an exponential function. Because don't exponential functions behave differently to the right or the left? Most functions, it's fine. The right end and the left end are going to be the exact same thing. It doesn't really matter. But with exponential functions, the AP loves to trick you because its right end behavior and left end behavior are very different. So if I was to rewrite this, in a way that we understand a little bit more, wouldn't I do x squared plus 1 over e to the x? What do you guys think? Is that good? Cool. So if I was to write that, thinking about the right end behavior model, that's as x approaches positive infinity. Left end behavior model is as x approaches negative infinity. Are we good? I could write the word as, I'm just being lazy. Right end behavior model. What would I say? What would I do? How would I write it? What's going on as I go to the right and as x increases without bound? Who would my g be? big, which means 1 over 10, 100,000 million, just as an illustration, would get infinitely small. This is going to have less and less and less and less and less significance, but what's going to stand the test of time? To the right. X squared. Its magnitude is stronger. X squared will determine what's going on to the right. However, as I go to the left, as x is approaching negative infinity, maybe this or maybe even this, what happens if I think about plugging in higher and higher negative numbers? Isn't that going to be e to the negative times the negative will be positive? So who's going to win over x squared or e to the now positive x? So now my end behavior model is going to be e to the x. Right? And so what impact does that actually have? Well, if I was to go ahead and, taking these end behavior models, if I want to take the limit as x goes to infinity going to the right of x squared plus e to the negative x equals, I would actually want to look at, my brain can't necessarily process this whole thing, I think of it piece by piece, but in essence when I had you guys think about plugging in higher and higher values, that goes to 0, I actually had you looking at the right end behavior model and saying, hey, ignore him, he doesn't really matter, look at him, and what's he doing to infinity? Going to infinity. So what the right end behavior model does is the exact same as what the function does. So I can mimic the answer and say, hey, I can use that. We'd have to make a statement about it if we were to do it in a very, very proper way. And say, since this one is infinity, then that one's infinity as well. But what's going on as I go to negative infinity? Technically, you're going to be looking at e to the x, but here's the crazy thing. Aren't you going to be looking to e to the x as x goes to positive infinity? Because if you plug in a negative, it's really a positive. So, oh, just think about e to the x as I plug in bigger and bigger numbers, because a negative times a negative is a positive. That's going to grow. That's not going to matter in light of the stronger guy, e to the x. Now, ironically, what's true either time, this time? Yeah, they end up both going to infinity. However, in other problems, and you guys saw them last year with an exponential function, you can have drastically different answers going to the right, going to the left, because sometimes the end behavior models are different. Trisha? Yeah. You guys, sorry, I can leave whenever you need to. Trisha, did I give you that check? No. It's back here. I didn't have exact. And the last thing, seeing limits as x goes to positive or negative infinity. I've kind of used this a few times on you guys, but without forcing you to actually show the notation. Let me zoom out a little bit. There is another way of looking at infinities based on the context of the problem, if it's helpful. These are really light. I'm sorry, guys. I don't know why they're so thin. Let me turn off the front light. So as we're approaching infinities, especially if we're dealing with quotients, and to keep it general without getting to a specific example yet, if we're approaching x approaching infinity of an f of x, we can actually rework that by basically thinking of u sub. Is one way of thinking about it. But we can rework our thinking. Instead of thinking of going to infinity of f of x, we can actually come towards 0 from above of 1 over x. And if that doesn't make sense, consider the graph of 1 over x. As I come towards 0 from above, as x is approaching 0 from above, where's my function 1 over x approaching? Positive infinity. So that's kind of how I'm able to make this substitution. In a sense, I'm making this the limit as u goes to infinity of f of u and letting u equal 1 over x. That's one way of considering it. If I'm trying to go to negative infinity, I can actually come towards 0 from below for 1, or using 1 over x. which might not seem to make a big difference until we get to an example like this. And we're trying to show why the answer is what it is. Another way of looking at it, which might or might not help you in this specific problem, but we could see coming towards positive infinity, 1 over x goes to positive infinity as x goes to 0 from above. And I could make it sine of x. So if you needed to visualize sine of 1 over x, that's actually really hard, but visualizing sine of x is really easy, and as you come in towards 0, well, the whole thing is approaching 0. But I know some of you can plug in infinity, or think about approaching infinity and say 1 over infinity is 0, sine of 0 is 0. But this has a justification or a reason as to why. Without just a, oh, okay, I kind of get it. But this one we could also change as well, because this one we could say if we're coming in towards 0, which is a little hard because then it's 0 times sine of 1 over 0. 1 over 0, isn't that like an infinity thing? And then sine of infinity doesn't exist, and times 0, like, ugh. Now some of you know how to rework that and make that pretty, but we could also rework this by having this be the limit as x goes to infinity, positive infinity of sine of, you would flip that, it's the reciprocal, x over, and then you would flip that, so it'd be 1 over x. And you could do the limit as x goes to negative infinity. So you have to kind of do like a piecewise sort of limit, because you actually have to think about from above and below and make sure they agree. But I think most of you for this one, if you're able to see it, you might stick with the way that we did these crazy ones last year, which is this is x over 1, you can divide by the reciprocal, and as x goes to 0. Wait a minute.
It's the problem from yesterday.
Huh?
Isn't that the same problem from yesterday? We did on the board.
Mm-hmm. But I don't think it was written this way. I think it was written that way, wasn't it? Was it written that way? I don't know. Do you guys notice there's a sign of u over u? And so you can be like, hey, it's just 1, right? But don't we have to have u approach 0 and 1 over x approaching 0? Isn't that the same thing as x approaching infinity? Is this answer 1? Is this answer 1? Anyway, we're at the end of the section. You guys go ahead and tackle homework. We're left on this one example of, I don't want to just give you an answer, so then you ponder it a little bit tonight. What is the answer? 1? Infinity? 0? Because the formula would say 1, as long as the formula can be applied.
I did.
This one's hard for my brain to understand. This one's easy. Because formula says sine of u over u. U has to approach 0, which would mean x has to approach infinity. The formula doesn't work. See it? So then check this. Yeah, it doesn't match. So it would need to be 1 over x approaches 0, and then we have to get to here for the formula to work. So that's why it's not 1. But then check it. If I just rewrote it, what happens as x grows? to stump you every now and then, because usually you understand it. Hi, Ivy. What's up? Hey.